Hi everyone. Thanks for coming to the Temporal Graph reading group today. So we are glad to host Zifeng from University of Cambridge, who will be presenting his recent work, DyGMamba, efficiently modeling long-term temporal dependency on continuous time dynamic graphs with state space models. And yeah, so I will do some intro for Zifeng. So Zifeng Ding is a research associate or postdoc a researcher at the University of Cambridge, and currently he is working with Prof. Andreas Vellatros in the Cambridge um, NLIP group. His research interests include temporal reasoning with LLMs, multimodal fact-checking, LLM hallucination detection and mitigation, and synthetic data generation for LLMs, and representation learning on structured data, um, as well as temporal and dynamic graphs. So I will hand the mic to you, Zifeng.
Yeah, let me share my slides here.
Yeah.
Okay. Yeah, I'm just sharing this.
And
Um,
and do you prefer us to ask question during the talk or at the end of the talk?
I don't mind. If you guys really have something on your mind, can just shoot me the question. It's fine. Yeah.
Okay, sounds good.
Yeah. I hope you can see my slides properly. Yeah.
Yes.
Yeah, yeah,
Yeah.
okay. Then I will start. Sorry, I didn't have enough time to prepare this presentation. I just finished the PowerPoint yesterday. I hope everything is fine. So welcome everyone to look at our kind of recent work, DyGMamba, efficiently modeling long-term temporal dependency on continuous time dynamic graphs with state space models. So first, let me give you a short introduction and background. Um, we see that actually, as stated in my title, we are dealing with the dynamic graphs. So dynamic graphs, they are the graphs that store node interactions in the form of links labeled with timestamps. And there are two types of dynamic graphs. First are the discrete dynamic graphs. We call them DTDG. They are a sequence of graph snapshots observed at regular time intervals. And we also have CTDGs, continuous time dynamic graph, which can be represented by a stream of events where each of them is observed at its own timestamp. And on the right side of this slide, I just took these two pictures from a recent paper. So they are saying the differentiation about the definition between the DTDG and CTDGs. And we can see that CTDGs can naturally preserve more temporal details because every interaction can be tracked with its own timestamp. So why we focus on this? And then you might also notice that in the title of this talk, we have modeling long-range temporal dependency as our topic. So we're trying to ask, is it necessary to model it? So we think it is yes. There are several reasons. First is that we have actually put here some statistics about the number of available historical one-hop neighbors for each interaction in 7 real-world datasets. And we have seen that we actually have abundant historical information in real-world datasets, and we can try to maximally utilize them. And we also noticed that there are several works trying to start to pay attention to the long histories. And at the end of this presentation, I think I will also show you some experiment about increasing historical information will actually help CTDG modeling. So as I have mentioned, there are several works have done that. So first, let's talk about the problems of previous works. Um, we take a look at two recent models. First is DyGFormer. It uses transformer to model the sequences of one-hop temporal neighbors. The good points are that it can model very long interaction sequences, and it also shows very good results. However, the scalability is compromised due to transformers' quadratic complexity. And another work is from last year's ICML. It's called CTAN. It tries to capture the long-term temporal dependency by propagating graph information in a non-dissipative way over time with a graph convolution-based model. And the strength is that it is highly efficient and it also considered the multi-hop neighborhood, but it fails to capture very long historical information, and it is outperformed by DyGFormer without computation constraint. So based on this analysis, we have summarized two challenges. So first challenge is that how to efficiently leverage the long histories. We try to solve this challenge by introducing Mamba. So we will use a state-based model to encode very long sequences of temporal neighbors. And what is Mamba? I'm not going into a very detailed discussion about what is Mamba. Just bear in mind that it is a recurrent style of sequence model unit, and the parameters at each step of sequence are decided by the input. And the most importantly is that it can help us to avoid the quadratic complexity of transformer. And here is the second challenge is that how can we effectively select the critical temporal information in long histories? We try to solve this challenge by modeling some so-called edge-specific temporal patterns, which is defined in our paper. So let's take an example to show what are the edge-specific temporal patterns. For example, I asked a model, will I still frequently listen to the song One Step Closer in 2024? The answer is not really, because it was a song released very, very long time ago. However, maybe in the history, we see that on January the 3rd, 2010, 1803, I was listening to this song. And then after 2 hours and 12 minutes, I was listening to this song again. And next time I was listening to this song was on January the 20th, 2020. It was at 10:23. And we found that actually the frequency of me listening to this song is actually changing. And after that, maybe I haven't listened to this song for a really, really long time, and I'm trying to predict whether I will be listening to One Step Closer on October the 25th, 2024. If the model cannot know that I'm genuinely like not listening to this song too much, it will actually likely to say, yes, you're listening to this song at this timestamp because it has seen that I have been listening to this song for a really, really lot of times. But actually, I'm listening to a new song from them. So it's the Emptiness Machine, which was just released very recently. So if we can capture such kind of change of frequency, we can actually help model to do the better prediction. So we can try to capture such patterns with another sequence modeling unit that can help us to encode the sequences of the time intervals. So then let's see what DyGMamba does in this work. First, it is the first work using SSM for CTDG modeling, and it can demonstrate high efficiency and strong effectiveness at the same time. It also helps us to find that actually modeling temporal patterns is the game changer. We know that Mamba, in terms of performance, it is slightly worse than Transformer, but by modeling the temporal patterns, it can help the Mamba-based model to surpass the Transformer-based model. Let me also briefly talk about two definitions. So first, what is CTDG? It is just as I have stated in the first slide of this talk. But more formally, we can define a CTDG as a sequence of chronological interactions here. It is just a set of tuples. Yeah. And U and V are the source and destination node, and we also have the timestamp of each interaction. And for attributed graph, we have the node features and the link features. We can also call them edge features. But if the graph is not attributed in our work, we will just set these features to 0 vectors. And we try to study the downstream task of representation learning, which is called the dynamic graph link prediction. So given a CTDG, a source node, a destination node, as well as a timestamp, we try to predict whether this interaction exists or not, but we can only take the evidence or the hint from the previous interactions. So next, let me show you what DyGMamba looks like. So here is the model overview. We can take a look at the figure here, which is the pipeline of our method. So more specifically, if we want to predict the potential link UVT, step 1 is that we try to find the one-hop temporal neighbors of them. And for U and V, we take the neighbors of each of them as a sequence and encode it with a node level SSM. And then we take the historical interactions between U and V and try to compute a sequence of time intervals of neighboring interaction pairs, which is just about temporal patterns. And then we try to encode it with another SSM block. We call it time level SSM to model temporal patterns. And next step is that we try to dynamically select the information from the output of the node level SSM by considering the output of the time level SSM. And we can get time-aware representations for source and destination nodes at the prediction timestamp. And finally, we try to use a MLP to judge the existence of the link. So first, let's see how we encode the temporal neighbors. We will treat the temporal neighbors as the temporal nodes. For example, here, this SUT, SVT are the previous historical interactions. And we try to transform into one-hop temporal neighbors by denoting them with this NEIUT and NEIVT. So each temporal neighbor will be including the node as well as the timestamp. And we then try to encode each neighbor into representation. We know that some graphs, they have node features, some graphs, they have edge features. So we just take them and stack them into some kind of feature matrix. And then we also have the time features here. We are just reusing the previous time encoding function from TGAT, which is here, I cited here. We try to compute the time feature for every neighbor. And also we try to include another type of feature called node interaction frequency feature. It is the frequency of neighbor nodes in both source and destination nodes neighborhood. It is also just like reusing the previous work's results. So also we have used another technique to try to save the computational budget. We call it patching. Actually, it's not we call it patching. So patching was proposed originally from DyGMamba. It is used to cut the computational consumption. Why it can cut it? Because it treats p temporally adjacent nodes as a patch and flatten their features, which means that the sequence length will be compressed by p times, which is very useful in transformer because it has a quadratic complexity. But when we do this, we can actually save computational resources, but we will be at the cost of mixing neighbors, which means that we will lose some temporal details. And I will show some experiments about it in the later slides. So then let's see how we try to encode this sequence of temporal neighbors with the SSM. First, we will map these features with MLPs to another dimension. And we try to transform node features into representation metrics by concatenation. And we encode with this SSM function. I'm not going to explain what is it. If you know Mamba, if you copy their equations and try to read their code, you will understand what it is. But by 2 minutes of explanation will not help here. So it actually looks scary, but it is just how Mamba deals with the sequence of vectors. But we need to know that since we sort the temporal neighbors chronologically, when we try to put it into Mamba to do the recurrent style of modeling, it can naturally learn the temporal dynamics for graph forecasting. So after that, let's see how we learn from temporal patterns. We have mentioned that we have proposed one time level SSM. So this is the step-by-step pipeline of this module. First, we will find out k-temporally nearest historical interactions between source and destination node before the prediction timestamp. And we also try to sort them in the chronological order. So then we compute the time difference between each neighboring pair of them and get a time difference sequence. And we see that there is another sequence. So we can also try to formulate them into some representation vectors and then input into our time level SSM. So how we do that is that we try to input this time difference into time encoding function I have mentioned in previous slide to get an edge-specific time feature vector. And we stack these features into a matrix here, we note it as capital H UVT, and map it with another MLP and input into the SSM to capture the change of the time intervals. So here, these 1, 2, 3, 4, 1, 2, 3, 4, 5, 5 equations here is just as same as how we did in the node level SSM, but now the input is the time difference sequence. And in the end, we will compute some representation of the temporal pattern denoted with this lowercase HUVT by mean pooling over the rows of this matrix. And we should note that K here, let's say we only find K temporally nearest historical interactions, and K here is a very small number compared with the sample neighbors. For example, in a real-world dataset Enron, we sample like 256 temporal neighbors, but K, we only take 30. So it means that we actually won't increase a lot of computational resource consumed during this process. And we compute this compressed representation to represent the edge-specific temporal pattern. And after we have this representation of the temporal pattern, how can we achieve this dynamic information selection? So we use this pattern to dynamically select information from the encoded temporal neighbors, which is the output of the node level SSM by using these functions. So here, several points need to note is that first, for notation, here's theta can be either the source U or the destination V. And actually, the output of this dynamic information selection, we call it a time-aware node representation. So it is just the weighted sum of its own neighbors. But how can the weights being computed is that we try to compute the selection weight by combining the temporal patterns as well as the opposite node. It can help us to strengthen the node connection. For example, when we try to compute the selection weight of U, we will try to derive this selection weight by considering the temporal pattern as well as the historical information from node V. So after we get this time-aware node representation, we input it into another output MLP to increase the model's capacity. And for parameter learning, we just use the binary cross entropy, which is a very standard loss function. And we derive a MLP-based model prediction network, feed-forward neural network, to get the probability of the existence of a potential interaction. Next is the interesting part. We finally get rid of these math calculations. Let's take a look at the experimental results. First, for the datasets we have considered, as we have mentioned before, 7 real-world datasets: Last.fm, Enron, MOOC, Reddit, Wikipedia, UCI, Social Evolve, which are very standard CTDG datasets. And the first 3 are long-range temporal dependent datasets because they require more temporal neighbors for optimal modeling. And for baselines, we also considered 2 types of baselines. First are the baselines designed for long-range temporal dependency, which are DyGMamba and CTAN, and the other ones, Jody, DyRap, TJAT, TGN, CAW, and EdgeBank, TCL, and Graph Mixer. If you are doing dynamic graph, you will be very familiar with them. So for the evaluation settings, we try to evaluate our model and baselines on 2 types of link prediction tasks. First is the transductive link prediction, and second is the inductive link prediction. And we also follow previous work by evaluating the models on the negative sampling strategies. First, the negative sampling strategy is called random, which means that we randomly sample the negative edges. And second is the historical. We sample negative edges that were positive at previous timestamps. And inductive, we sample the negative edges that were positive at previous timestamps during evaluation. Here is the benchmark result on real-world datasets on the transductive link prediction. We found that our model can achieve the best rank, average rank. It shows more superiority on the long-range temporal dependent datasets, for example, the first 3 datasets in this table. And for the inductive link prediction, we also observed the same trends, so the conclusion still holds. And for the ablation study, we have done A, B, C, D, E, F with 6. It's a lot. So first, we try to remove the time level SSM in variant A, and then we remove the node level SSM in variant B. And in C, we try to use a softmax function on each node's own history for dynamic information selection, while in variant D, we try to use the same softmax function, but now it is on the opposite node's history for dynamic information selection. We should note that variant C and D, they both do not use any temporal pattern for dynamic information selection. It just introduces extra parameters for learning from the data's pattern. And in variant E, we try to remove the time features in the neighbor encoding, and variant F, we try to remove the node interaction frequency features in neighbor encoding. Um, these two tables are showing the transductive link prediction and inductive link prediction results for our ablation study. We have several findings. First, from variant A, we see that it is outperformed by our model, so it means that modeling temporal patterns are useful. And also in variant B, we see that encoding graph dynamics with SSM is contributive. And third, we found that the dynamic information selection is important because variant C and D outperform variant A in most cases, even if they are not using the temporal patterns. And then we found that information selection from opposite node is beneficial, which means that we can actually strengthen the bound between the source and destination nodes, and it will help us in modeling. It's because we noticed that variant C generally lags behind variant D. And also we have found that information selection with temporal patterns is useful because we see that variant C and D trails our complete model. And in the end, from variant E and F, we found that node and time and node interaction frequency features are actually important. To further demonstrate the usage of temporal patterns, we try to construct three types of synthetic datasets, and we try to take a closer look into our temporal pattern modeling unit. So these three synthetic datasets are S1, S2, and S3, and each dataset has only 7 nodes, and each pair of nodes follow a temporal pattern. For example, in S1, the time intervals between neighboring interactions follow an increasing trend with a velocity of 0.05. And for S2, it is with the same velocity, but now the intervals are following a decreasing trend. And for S3, we try to modify S1 by repeating several periods of increasing patterns taken from S1 to form a periodic dataset. And here, these three figures are just showing the time intervals through time of 3 datasets. And we try to evaluate the model on this transductive link prediction random NSS setting. The results are shown in the following table, and we can find that actually DyGMamba greatly outperforms DyGFormer and CTN. And variant A, C, and D, they do not use temporal patterns. Even if C and D, they did some dynamic information selection, but they fail to model temporal patterns. That's why they are struggling in capturing patterns in synthetic datasets. And we also trying to think, does temporal pattern modeling help on real-world datasets? Because previously we only show that it works on synthetic datasets. So what we do is that we try to develop another variant called variant G by switching transformer in DyGFormer into Mamba. So if we take a look at the results here, we see that variant G is outperformed by DyGFormer constantly. Yes, DyGFormer constantly, yes. And we see that actually after we have equipped our model with temporal pattern modeling, the DyGMamba can outperform DyGFormer constantly. So the finding is that the temporal pattern modeling, we think it is the game changer because it can make the Mamba-based model surpass the transformer-based model. And after we have seen a lot of experiments about performance, now let's see how DyGMamba is efficient compared with previous model. So we try to study the model size per epoch training time and GPU memory, and we try to compare them across various models. So here are the figures here. They are actually these statistics on 4 datasets, Last.fm, MOOC, Enron, and UCI. And we have this shaded green pattern. The greener the points is located at, the better the overall balance between the effectiveness and the efficiency. So we find that DyGMamba can constantly hold a good balance between the effectiveness and efficiency. And we also find that CTN, well, it is extremely efficient with these metrics. But when we were doing experiments, we found that actually CTN is a little bit hard to converge. That's why it even performs well on this per epoch training time. It doesn't mean that in total the training time will be still low. So we try to do another comparison about the total training time among DyGFormer, CTN, DyGMamba. And in this table, we have shown the statistics. Here, this TOT on the third column is the total training time, and TEP is the per epoch training time, and in the middle is the number of epochs to get to the best performance. And we found that CTAN is a little bit uh, unstable in our experiments with a fluctuating convergence speed. And overall, DyGMamba is a good choice regarding the total training time. And after that, we have also studied the impact of patch size on scalability and performance. Notice that I have mentioned patching might introduce some problem. So let's see how patching will be impacting a model's behavior. So DyGMamba and DyGFormer both use patching, and on Enron, we are sampling 256 neighbors and using patch size of 8. So the sequence length in the transformer on Mamba will be 32. And now let's think, what if we can assign more computational resources, which means that we can decrease the patch size and then the sequence length will be increasing. So we are evaluating both models on Enron with patch size varying within 8, 4, 2, and 1. And here are 4 figures showing the performance of both models, the number of parameters of both models, GPU memory, as well as the per epoch training time. We also have findings that as the patch size decreases, we found that DyGMamba always consumes fewer parameters, and the speed of increase of computational resources, for example, on GPU memory and per epoch training time, is much slower on DyGMamba. And our model can also achieve better performance while DyGFormer performs worse, which is quite weird. So we paid further attention to this. We're trying to discuss why DyGMamba performs better even when the patch size is smaller. So notice that with smaller patch size, we have a smaller projection layer in patching, means that we have fewer parameters for training. It will definitely lead to lower model capacity. But smaller patch size will mix fewer temporal neighbors, which means that we can preserve more temporal details. This is what we want. So to further study this, we try to benchmark also the variant A's performance. Remember, variant A is just DyGMamba's variant without modeling temporal patterns. And we found that variant A can reach a plateau and drops afterwards, which means that there is a trade-off between the advantage and the disadvantage. And we found that DyGMamba constantly performs better, and we think that it is because the dynamic information selection with temporal patterns will help us to better leverage extra temporal details. Next, and an additional study is that a lot of people really focus on this question. Does modeling longer history really help? So what we did is that we tried to rerun the experiments on 5 models, DyGMamba with 4 baselines, by increasing the sample neighbors on this dataset from 8 to 256. And we try to limit the total training time to 120 minutes. And if you take a look at this figure here, you see there are some points marked with crosses and there are some dashed lines. So the points with crosses connected with dashed lines are the ones that exceed time limits. So the finding is that most baselines cannot finish training when there are too many neighbors, which means that the efficiency of DyGMamba is very good. And we also found that DyGMamba and DyGFormer can benefit from longer histories. So we think that we can conclude actually the key issue is not whether increasing sample neighbors is always beneficial, but rather whether a model is robust enough to effectively process larger amounts of historical information, whether a model can distinguish the important information from the redundant one. And we also discussed where our model can excel and where our model will fall short. We first found that our model is very good at modeling long-range temporal information. And also, our model is very good at, in some cases where there's a clear temporal pattern. Remember our synthetic datasets, where the density of repeated edges follow a specific trend. However, it also is bad at some cases. We found that under historical and inductive NSS settings, particularly when the number of available one-hop temporal neighbors for nodes in the link prediction query is limited, DyGMamba is not performing very well. So we present here the statistics of the number of available historical one-hop neighbors. For example, the worst cases DyGMamba was performing are the historical and inductive NSS settings on datasets Wikipedia and UCI. If we combine these results with this table here, we can find that in Wikipedia and UCI, we have a limited temporal context. And we think this is the reason why DyGMamba cannot perform very well, because it requires a very long history for modeling. And finally, I will give the discussion of, do we really need the multi-hop information? This is also another question a lot of people pay attention to. So I think it is yes, definitely. Because we have seen CTAN achieving extraordinary results in some settings. However, by introducing multi-hop information, we will definitely face several challenges. First is that we will increase the computational cost. In this work, we want to do it efficiently, so we didn't try to do that in our work. And second is that making sampled temporal neighborhood, it will make the sampled temporal neighborhood concentrated on the temporally closer positions, which will be losing the farther hints. This can be seen in this table here. So in this table, we try to sample one hop temporal neighborhood only, or we try to sample the one hop plus two hop some mixed temporal neighborhood. But we try to fix the sampled neighbor, the total number of the sample neighbor as same as each other. So in this way, we try to maintain the computational resource. For example, we have only one hop temporal neighbors in 256 neighbors, but we can also try to split one part of them, take one part of them outside and try to put them in, try to put some two hop neighbors inside. And then we try to track the maximum time difference between the temporal neighbor and the prediction timestamp. We can find that on the right column of this one hop plus two hop max time difference, we see the number is much smaller than the one hop only max time difference, which means that when we try to sample the mixed hop under a limited computational budget, the temporal neighborhood will be concentrated on the recent history. So the last problem is that modeling multi-hop information will require additional modules to differentiate information from different hops. And we have found that, for example, our baseline CTAN and CAWM, they both consider the multi-hop information, but in most cases, they cannot beat us. We think that actually it's because their model capacity are not strong enough to optimally differentiate information from different hops. However, despite these drawbacks or challenges, we think that it is really a nice future direction still. Yeah, that's all. Thank you very much.
Yeah, and thank you for the presentation. I think you raised your own hand as well. When you're,
Me?
yeah, I think
Oh,
you raised your hand. But yeah, thanks for the nice presentation. So definitely a lot of experiments. I do have quite a few questions, so I can start. But for the audience, if you have any questions, feel free to type in the chat or just unmute yourself. Um, and yeah, so there's a lot of experimental insight. So first of all, it's not surprising to me that when you are doing historical negative sample, the number of sample neighbors do matter because literally that task is testing basically how you can understand the difference between historical information and current information, right? Because it's sampling from the same historical set of neighbors. So I think that makes sense. Um, have you tested with a setting that's not treating the link prediction as binary classification? Because um, I think that could be one of the reasons why the performance is so high on these one hop models, because if you are using one negative sample per positive sample, in general, the task is much simpler than if you try to rank the positive sample across like many different negative samples. Um,
uh, I'm just thinking, what do you mean by transforming the binary classification into harder settings? Do you mean that should I follow something like in temporal knowledge graph, like try to predict a list of nodes, which node is the best?
exactly.
I never tried it. Actually, this is the first work I'm doing pure dynamic graph. I was doing
Okay.
temporal knowledge graph, you know that.
Okay.
So I am not sure. I think it will be completely different. I also know that you guys having this. Did you guys do it in TGB too, right? You guys did it, right?
Yeah, so
Um,
in TGB, we always use MR instead of
yeah, yeah,
the
yeah.
binary metric. Yeah,
Yeah, I read that paper. I was not trying to fix that because I was using the repository from DyGFormer. I think it is worth studying, and I think maybe the results will be completely different, and conclusion will be more, how to say, comprehensive compared with the conclusion here. I understand. So for binary classification, it is a little bit too easy. Yes, that's true. Yes.
yeah, and well, so yeah, so I think it's like so it's not specific to your work because in the past most of the paper are doing this binary classification, which is kind of an artifact that when people started doing temporal graph research and the models are not very efficient, so the best they can do is do this kind of evaluation, which works, but it tends to lead to oversaturated performance. And
Mm.
that could be one reason to explain, because with one hop information, if you can already get 99% performance on this binary classification, then there's no room to show that multi-hop helps, right?
Yeah.
Um,
Yeah, and also another thing it just pops up is that I think why using MRR is better is because you're trying to differentiate between a lot of hard negatives, right?
exactly.
Not like only the
A
the
single one, yeah.
yeah, and the false and the negative edges are only sampled like one for each positive edge, which is not enough, I think. But if you sample more, it will have some bias. I don't know. I think
Well,
MRR.
you have the bias, but for example, on the wiki on the TGB we basically sample all possible negatives.
Yeah, yeah. Yeah,
Is
that
ranked
makes sense.
one out of
Yes.
1,000, so there's no bias there. But of course, for much larger data sets, it's impossible to sample like 5 million negative per single edge for evaluation. So that would be too much. Um, yeah, but that's more a problem with the model inference and how you want to evaluate that. And then the second question I have is that you have different variants which have very interesting conclusions. Have you tried removing the neighborhood encoding scheme that you have? So you have something very similar to what DigiFormer uses for the.
Yeah.
So DigiFormer does the common neighbor thing, I think, and then in your case you do a frequency neighbor
Yeah.
sampling. Have
Yeah,
you
I did
tried
it.
like removing that information and see how the performance will
Yeah,
change?
it's in the variant F. Sorry, I have a habit of using variant A, B, C, D, E, F to denote my ablation study because ablation studies are very complicated. If I put it on the left side, it will be very long. So
Right, 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 right.
yeah, actually
Yeah.
in variant F, I was trying to do that.
Okay,
And it actually shows a very big performance drop. Yeah.
that makes sense because for link prediction, the kind of the joint neighborhood information, so the information surrounding the two endpoints are one of the most important things. So if you just add that, that's gonna boost any model's performance because it helps differentiate between different edges. Because for now you just have two node embeddings, but if you add this information, then it gives you basically identifier for specific node pairs.
Yeah.
So it helps the model to learn better a little bit.
Yeah.
Uh,
Yeah.
yeah, it's very interesting overall. How much do you think the model can scale? So in TGP, we
I
have up
didn't.
to like 80
Yeah.
million edges or something.
Yeah, it's a very good question. Actually, we also put in the main body of this paper about the GPU memory usage. I remember on Enron, if we fix the patch size to 8, we can actually put 8,192 temporal neighbors when we are modeling um, within a 45 gigabyte GPU, but the IG cannot. Yeah.
Okay.
So I only did this in the in terms of GPU memory. I didn't pay attention to like the for example you say like 80 million edges. It is actually a lot.
Yeah.
So I didn't test the time. What I did is that I ran some datasets on TGB. It was so huge, I gave up. So I
Well,
don't
thanks for trying. Yeah, I know
yeah
that takes forever to run, especially the DyGlib. If you're using the DyGlib,
yeah
which is the least optimized, well,
yeah.
yeah, it's because especially the checking the common neighbor stuff, it's very, very slow.
Yeah, it's very
like
slow. It takes forever, and I cannot
okay,
finish that experiment, so I gave up.
I
Yeah,
see.
yeah.
Um, that makes sense. Do you have some questions, Julia?
All right, no, no, thank you. Everything was clear.
Okay. And then I guess the final question I have is, how do you think DyGMamba will work for temporal knowledge graph? Maybe with some
Um,
small changes.
yeah, I didn't start to study this point from the perspective of temporal knowledge graph. I'm not sure, actually. First, we need to make sure that we can transform this model into a cross-entropy loss-based model, right? We need to do the MRR stuff. This can be done on your side, like, for example, from what you have done in your previous work. And then we need to incorporate the relation type, right? And
Which you can add as additional edge feature. The most naive thing is just to add it as
yeah,
edge.
which seems so, yes. And I don't think that modeling one hop temporal event with this is very helpful. I don't
Uh-huh.
think so. Yeah, I think for temporal knowledge graph, I still believe that the time-aware graph neural network is the best. Yeah, I still believe that. I don't think this kind of like event-based because I think temporal knowledge graphs are a little bit m much harder than most of these real-world CTDGs. What do you think?
Yeah, I think, well, these ones are the smaller data set.
Yeah,
So I think as like scalability is a different thing. But I think, yeah, I agree that multi-hop reasoning is probably a lot more important to get better performance from knowledge graph,
yeah,
um, because that's more inherent in the task. For link prediction here, like most of them are interaction data sets, so you really don't need that much multi-hop because you just check the user's past history and you are mostly good. But that's kind of more biased on the data set. And then if you have something like biological network or something, that could change. Or you're trying to do some graph level task, that could change as well. Um, but yeah, I think this is very interesting. I don't know how transformer-based architecture or like state-space model will work on knowledge graph.
Yeah,
it
sorry.
can work. Yeah, please go ahead. Yeah.
I was also already thinking, would this be easily transferable? Didn't come to a good conclusion yet, but if you would do it, I would be very interested in seeing or discussing the results.
Yeah, yeah. The thing is that I'm not sure whether I will be still doing temporal knowledge graph or not. But if you are doing, I will be giving you some suggestions. I think. Well, I think it can work. Sorry, actually, I'm very tired now, but it doesn't matter. I was trying to think hard how to transfer this to temporal knowledge graph. I think it can work. Um, well, because Andy just made a proposal, like he thinks that it can work by just incorporating the relation type as the link features, and but I'm just not sure the performance. I'm just not sure about the performance. I don't know, and I don't think proposing another work based on this type of work will get accepted anyway. So
Well,
for
not with the
industry,
one-hop neighbor stuff. And I
yeah,
don't think the one-hop neighbor can work for knowledge graph. I think you definitely need to do multi-hop, but potentially what I think could work is, yeah. So again, for the audience, we are going off track a little bit. So if you have questions, feel type in the chat. But if I were to design it, I will get rid of this one-hop stuff because it kind of annoys me a little bit that one hop is enough, um, which I think it shouldn't be. So if you want to do multi-hop, I think what you could do is you could do something like in static graph transformer. So you actually look at your knowledge graph, you compute some positional encoding like eigenvalue spectrum or something like that. And then you use that as in like encoding for your nodes, but you still use your transformer stuff. Um, so yeah, then you keep the time encoding and everything. So basically you are still able to do some multi-hop information
yeah,
from that perspective.
I don't know, Julia, you should know that there was one work very classic called SciGNet, right? Copy paste
Yeah,
net. It just
yeah.
reminds me of this work. I think this kind of one-hop information is just same as we are taking some repeated facts happening in the past.
Yes.
Yes, I think maybe in this way it can be something interesting. And also what Andy proposed by incorporating some multi-hop information is definitely useful in temporal knowledge graph. But how to combine them with Mamba, I'm not sure. I was criticized in iClear of this paper, let's be honest. This paper got 4.3 points in iClear. People think that I have no novelty. What I think is that for a research program, now people's taste has changed. If you just implement this new kind of modeling structure into dynamic graph, people won't buy it. I think if we can try to incorporate them with different kinds of ideas, for example, by combining the repeated facts with the multi-hop information, as well as introducing some very efficient method, maybe it will be a very good, yeah, project. Yeah.
Yeah, and people usually don't try, in a sense, continuous time with temporal knowledge graph, right? But like the data set itself is not continuous time, but the way you process temporal information can be continuous time. So what I mean is that temporal knowledge graph, you process snapshot by snapshot.
Yeah.
And continuous time, you get rid of the notion of snapshot. So you are just collecting past neighbors from the node, regardless of they are happening in the last snapshot or not. So maybe there's something going on there as well. Like you can do like multi-snapshot backtracking.
I actually see one paper just put on archive 6 days after my work. It is doing DTDG with Mamba. So if you want it, I can send you later on Slack.
Is that one of the other two? Like I saw two DyGMamba papers.
Yeah,
Basically,
yeah. It's good that I put like beforehand. I don't know that they are also putting it, but
yeah,
they have some theoretical flaws in it. I think it doesn't make sense, but I don't mind like they're putting it. So anyway,
yeah. Well,
yeah.
interesting. Um, and I guess just to remind, I think Julia, you also have another paper you hope to listen from Zifeng in the future. So
Yes.
Yeah, we can talk
you
about
mentioned.
it later. No problem. Yeah.
That sounds good. Yeah,
Yeah.
let's talk about that.
Okay. Yeah. So thanks for coming to the talk, everyone. I think like we all learned something and had some interesting discussion today. So let's thank the presenter again for presenting. And yeah, have a great day.